Okay, let's start. Hello, everyone, and welcome to this week's SAAO Colloquium. And today we are pleased to have Dr. Sasha Plavin from Harvard University. He is a postdoctoral researcher there, and he's going to talk about hunting neutrino blazars in the multimessenger era. Thank you, Sasha, for accepting our invitation, and the floor is yours.
Yeah, thank you, Nargis. Thank you, everyone. And also, I want to say that if there will be something like I need to react to, please just say it out loud because I probably won't see the chat anyway. And indeed, today I will be talking about the recent and still ongoing, actually, hunt for neutrino blazars and for understanding their properties. I will gonna go through the whole spectrum from large-scale statistical surveys to focus studies of individual sources. And observationally, my talk will definitely have a radio astronomy and VLBI focus, but it shouldn't require any kind of deep knowledge of the technique anyway. So yeah, with that I will start. And the neutrino sky, I mean, the neutrino astronomy is of course much younger than the electromagnetic astronomy, but the neutrino sky is already becoming very diverse. Today I will be only talking about the part of like AGNs and blazars as neutrino sources, but we definitely have other sources. At the very least, there is a Milky Way detection in neutrinos, and potentially there are other sources. The neutrino sky is really probably quite complex, the same way as electromagnetic sky is. So today I won't cover the whole neutrino neutrino source population, but only focus on blazars. And in the context of blazars and AGNs, so I'm actually an astrophysicist, not a particle physicist. So for me, the big question that neutrinos can help answering is what the AGN jets consist of. So in the electromagnetic emission, as it's typically observed, electrons and positrons appear to dominate in basically every band. Still, protons may carry a major part of the black hole energy. They can bring this energy further away, but they are very challenging to study observationally. Like if you're looking at electromagnetic emission, like hadronic signatures, they are very hard to distinguish from electrons or positrons. It's you need to have quite a bit of model assumptions for that. Cosmic rays, they are, of course, a direct tracer of the presence of protons, but they won't point us to the specific source because they are heavily bent and deflected by magnetic fields in the universe. So this leaves us the high energy neutrinos. Actually, it is really the only direct tracer of protons in the AGN jets. So within the standard model, there is effectively only one, like, or one and a half ways to produce high energy neutrinos at 10 electron volts to petaelectron volts. And both ways require high energy protons. Then it goes through charged pion production and decay, and the results in high energy neutrinos. This is really the only way. This means if we see high energy neutrinos from some source, we definitely know that it has high energy protons in there. And so here I show the typical kind of energy scales for the like in the context of neutrinos detected by the IceCube and other high energy neutrino detectors. In terms of electromagnetic observations and finding and selecting blazars, first of all, yeah, by blazar, I will just mean an AGN with a jet pointing towards us. So basically, like this is a AGN jet, and we are looking from very close to its direction. This is the whole meaning of blazar that I will use. And one of the most direct ways, arguably the most direct way to select blazars observationally is through radio interferometry. The reason why it is very useful for this purpose is that VLBI is the only way to directly resolve parsec scales in distant blazars. And when it resolves these parsec scales, it really selects sources with very bright emission at these scales. And it is so bright that the only way to get such a brightness is to experience heavy relativistic beaming. So it's kind of you select sources with very high parsec scale, very bright parsec scale emission, and they just have to be blazars, almost all of them. Actually, like there's definitely more than 90% of blazars in a typical VLBI flux density selected sample. So that's what kind of motivates why I focus on VLBI observations here. And overall, the story of neutrino blazar connection started with a single source with TXS of 506 already almost 10 years ago. It was bright, flaring across the whole spectrum. It was the brightest. It actually became the brightest in the like VLBI sky after neutrino, soon after neutrino arrival. It was quite a lucky coincidence as well, as it still remains the only individually significant association between a blazar and neutrino. So if you don't go to population studies in blazars, this is still the only one. And for me personally, as for like a radio astronomer who observes blazars, this is a typical blazar in the sky, really. It is like typical bright blazar. We have maybe not thousands, but at the very least tens or hundreds of similar sources. And that makes it a bit kind of strange that there is still no individually significant blazar neutrino association, and highlights the importance of population studies, really. So in the past few years, there's been quite a few, and like there's more and more population studies basically connecting blazars to neutrinos. Here I will, so this is just a definitely non-complete, but I think reasonable selection of those that use also radio emission as an observable tracer for blazars. And here I will like briefly like say a few words about our earlier findings, basically about associating blazars with neutrinos. And for that, we use the reasonably clean as possible sample of IceCube events. Still, even at these energies, there is no way to select it better than having about half of sources coming, half of the events coming from the background, not even from astrophysical sources. And by cross-matching it with a uniform sample of blazars all over the sky observed with VLBI, we get that the VLBI flux density of blazars coincident with neutrinos, it is higher, it is significantly higher than the average flux density of overall blazar, of typical blazar from the sample. And this can only happen really if blazars are really associated with neutrinos. They don't just happen to lay around by chance. And what's even I mean, I half expected it, but it was half surprising that after repeating kind of the same analysis with a difference of 3 years by gathering more neutrino data, we saw the increase of this significance roughly as expected. So this analysis was designed once, and then we repeated it after like 3-4 years, and the connection became even stronger. So I guess in a few years it will make sense to repeat the exact same analysis again to see how it goes. So anyway, the outcome of this result, and consistent with other studies that look for blazars around neutrinos, is that blazars that are associated with neutrinos, they are particularly bright, even among bright blazars in general. And this kind of already gives us at least some hint of what is the population of neutrino-emitting AGNs is, but we still need more details to understand the nature of neutrino production. I won't stop much on this, but there are more and more kind of studies of very different kinds of neutrino versus blazars. I'm particularly looking forward for more more details on like the future temporal correlation studies. Now it's these results are very preliminary and like kind of not extremely significant yet, but that's a thing I keeping an eye on. Also, there are some hints from smaller detectors like Antares and Chem3Net, Baikal GVD in the Lake Baikal. So I also won't stop much on this, but I'm happy to answer questions as well. So observationally, what we have now is that there is a growing body of observations in selecting AGNs and specifically bright blazars as significant sources of neutrinos at teraelectron volts to petaelectron volts. And I think we are now at the stage to try characterizing this source population in more detail. So one way to go is to focus on smaller samples. So yeah, the part I was just showing is really about the largest scales um, sample, like population studies of large samples of blazars as large as clean as we can. But to understand the kind of the underlying physics and nature of the neutrino production, we really need to have more measurements than just the flux density. And this requires kind of reducing our sample to sources that are well measured. And here I will focus on the these kind of geometric or kinematic properties of an AGN jet that are much more directly interpretable in astrophysical context than the flux density, and they are the Doppler factor, directly indicating the strength of beaming of electromagnetic emission. The Lorentz factor is the jet, just the velocity of the jet flow, and the geometric property is the viewing angle. So here I illustrate how a typical let's say typical VLBI blazar looks like. It's these parameters are the median from the really well measured, well monitored set of sources from the Mojave team. And you see that even a typical VLBI blazar, it's very highly beamed. You have a typical viewing angle of just a few degrees. The Doppler factor can enhances the emission. So the Doppler factor is about 15. So it's really like ultra relativistic flow pointing directly towards us. So now that we have a reasonably well-defined sample with kind of these kinematic and geometry properties measured, of course, what we want to do is to see how neutrino blazars fare in this context. And here I show, like, for each of these properties, the Doppler factor, Lorentz factor, and viewing angle, cumulative distribution. So the black line is the distribution of the whole sample of like Mojave, or we can think of it as all bright VLBI blazars. And the colored lines, for now, it doesn't really matter much. So which colored line we look at, they are almost exactly the same. And the colored lines indicate the only the blazars coincident with with IceCube neutrino detections. And you clearly see that all of these, no matter what parameter we look at, we see that these neutrino coincident blazars, they have higher Doppler factors. So kind of like the median would be almost 30, while it is less than 10 for the whole sample. It has higher Lorentz factor as well, and it has smaller. So here, just for the plot to look similarly, I just flipped the horizontal axis. So the viewing angle is indeed like smaller, and actually much smaller for for a kind of neutrino-associated, neutrino coincident blazar. And I was, oh, sorry. I was actually even a bit surprised to see the pictures so consistent. It looked even a little bit too good to be true, but after checking it with like different IceCube selection criteria, so one from that we used in the earlier paper, and then there is a more an updated IceCube catalog with some changes in the reconstruction. We see the results are about the same, and also when we play with VLBI like Mojave selection criteria, the result also stay qualitatively the same. So I would say that at this point, observationally, a very consistent picture emerges. The jets of blazars coincident with neutrinos are not just kind of have brighter, stronger flux density, but they are more highly beamed towards us. They have higher flow velocity, and they are geometrically just more aligned with the line of sight. And I would say that the kind of even though this is just the beginning of the kind of understanding and characterizing the neutrino-emitting population, this is already much kind of better and more direct than just the flux density. So yeah, this paper is now under review. I hope it should be published very soon, because we on the second revision we got very minor comments, but yeah, there's more details in there. Also, actually, it's important, like it can be instructive to see how strong the effect is, like how extreme these neutrino-emitting blazars are. So generally, like me and other people like doing VLBI studies, we are used to kind of these kind of properties being typical, and we already refer to them as very highly beamed, very extreme blazars. And in the bottom, I show the kind of median among the neutrino coincident blazars in the sample, and you see that they are even more extreme. So the viewing angle is actually just kind of comparable with an opening angle. So we are generally looking very close to the jet itself, all inside or almost inside, depending on the case. And yeah, they are like really very extreme. If you are working with non-Blazar agents, yeah, these are really the most extreme of the most extreme samples. And now we are probably not at the stage of really comparing how strong the beaming is for neutrinos and for electromagnetic waves, but it's clear that if you see the neutrinos from highly beamed blazars, it means that beaming also aids with their detection. Qualitatively, the same way as it does with electromagnetic waves, but quantitatively, I hope we'll be able to say in a few years. Maybe it's even a bit more extreme, maybe not. That we will see in the future. This part was kind of like intermediate in between very large samples and individual sources. This is a smaller sample of well-measured and well-monitored blazars in the Mojave. And here I will also show a very neat example that we only recently noticed, and the paper is also almost accepted. We also got minor comment recently. Is that so? This is the stacked map of IceCube at a bit lower energies. It's computed from IceCube computes it from slightly different sample of events. So this is not exactly the same events as I showed before, but it has three hotspots here, so first of all, two out of the three hotspots are bright blazars, and this one is number two. This is the second highest hotspot in the IceCube stacked map, all-time stacked map. And this blazar is actually very unique. It's it may not be like the brightest in terms of just the flux density, but it shows a very peculiar structure. So first of all, I mean, I guess I mean I don't know if you have like experience looking at VLBI, typical VLBI images of AGN jets, but this one it has a very wide opening angle. It gets very apparent if you look at it, and a wide opening angle is generally only possible if we are looking from inside or from the very close to the jet cone itself, just geometrically, because jets intrinsically are very thin, of like on the order of 1 degree. So to get a very wide opening angle, we have to look very close to the line of sight. And moreover, when we look at the polarization image, this is the core effect, like coinciding with this bright point in the map, and there is this kind of like linear polarization strongly hints at toroidal magnetic field. You see these kind of magnetic field lines direct, like circling the whole, basically the whole image, and they are directly propped by linear polarization. To make this image, I just rotated linear polarization ticks by 90 degrees to indicate the magnetic field. And this is a very striking case. Even like in general, there is not a lot of such sources, and it happened to be the top two in the IceCube all-time stacked image. So this source, I mean, I think this source should be a very kind of nice individual case where one can study the properties of highly beam neutrino-emitting blazars better than with a whole sample. And yeah, it looks very striking. Actually, after seeing this image, we started kind of digging into the into our VLBI archives and looking for similar sources with similar morphology unrelated to neutrinos. We found like just a few, and this one is definitely the most striking. So this is really a very unique source where we clearly see all these kind of the insides of the jet, really, and it happens to be coincident with the second highest IceCube peak. So yeah, observationally, this kind of concludes the travel from large scale samples all the way to individual sources. So now let's move to understanding what it really means. I will focus on mostly GN astrophysics because this is a part I'm generally interested in doing. So we see observationally that there is a whole population of blazars with non-isotropic neutrino emission, just because we see neutrinos from highly beamed blazars, and it already constitutes a major, again, noticeable fraction of the overall neutrino flux. It means that there is a whole population of these sources emitting neutrinos along the jet. For neutrinos to be emitted along the jet direction, we necessarily need the original protons to have also some momentum, so some kind of bulk relativistic motion along the jet. And this already puts some kind of like model-independent requirements or restrictions on the acceleration mechanism of protons. They either need to get this bulk kind of motion along the jet immediately when accelerating, or there should be some mechanism to accelerate already ultra-relativistic protons to gain their bulk motion. From the jet kinematics of the plasma flow in general, we know that the bulk motion is like the fastest ultra-relativistic bulk motion is generally attained at kind of sub-parsec and parsec scales, not immediately close to the black hole, but somewhere along the jet after the acceleration and collimation zone. So depending on depending on how the protons get this kind of bulk motion along the jet, if it is consistent with the overall plasma flow, then it puts a natural constraint on where the neutrinos can be produced, probably like not extremely close to the black hole. But also like the lower limit on how close the neutrinos can be produced to the black hole is still kind of debatable, and it's still not a kind of fully established thing. But the upper limit seems pretty clear, like because so given that the parsec scale emission properties and beaming and everything seems to be like to date seems to be the strongest observational tracer of neutrino production, and also given the hints for temporal correlation, we really can definitely state that neutrinos are coming from the very central parts of the AGN, not from radial lobes or something, but like from really central parsecs or tens of parsecs. Okay, so this is a kind of qualitative understanding. As for more quantitative statements, now of course we are heavily limited by the observational data, but I will show some like kind of attempts on the work in progress how we can quantify the neutrino fluxes on the basis of population studies. So this is the same plot I was shown before, indicating that neutrino blazars they have a stronger radio flux. They are brighter in the radio than an average blazar. This means there should be some connection of neutrino flux and radio flux. So assuming there is some kind of unknown power law between directly observed VLBI flux and not directly observed neutrino flux, I just fit it to the neutrino events and the radio fluxes, and this is the fit I got. So on the horizontal axis, we get the VLBI flux densities that is directly measured, and I just highlight where some of the kind of generally well-known blazars lie on this line, and on the vertical axis on the left, I show the kind of neutrino flux in terms of expected number of events detected over the whole IceCube lifetime. And you can see that even for the brightest sources, even for the brightest blazars, assuming these power law dependency holds, we expect much less than one neutrino per IceCube lifetime. This is very consistent with the fact that we don't really see any multiplets, so like two events reliably associated with a single source at the highest energies of neutrinos. So yeah, it's totally consistent with each source just emitting much less than one detectable neutrino. And the only reason why we see the signal from blazars at all is that because we have thousands of sources here and like hundreds in the right-hand side of the plot, and only together they form a neutrino signal. Yeah. Also, given this kind of neutrino flux, given a way to estimate the neutrino flux, we can try putting it onto the overall SED of bright blazar. So here are just some sources that have at least one kind of high energy neutrino events coincident with them. And this is just for comparison, estimates for that IceCube provided for TXS of 506 in their original paper. They are not really grounded in any kind of direct flux measurements for neutrinos. They are just based on like a single neutrino detected. So this one, the top one corresponds to one neutrino per half a year, and this one just corresponds to one neutrino per 7 years. These were the two estimates that were given in the original paper. But in the context of what I was showing, that we generally see much less than one neutrino on average from a source. We can plug the VLBI fluxes into the power law and get these flux measurements, so including TXS of 506 here. Of course, these are like very uncertain on this power law, and this is more of a phenomenological description, but arguably it is a little bit more grounded in the kind of in the actual fluxes than the arbitrariness of the kind of assuming one neutrino comes every like half a year or several years. So these also agree much these fluxes are much easier to reconcile with what we know from electromagnetic emission here. So maybe this is a way forward for the near future until we get like much better neutrino astronomy, like really to go with population studies like this. Kind of summarize in a sense what we understand, like how neutrinos actually helped us what they helped us to understand about the jet physics is here I provide like one also qualitative explanation of how all the related observables can be connected together. So just to remind you, to produce a neutrino of hundreds of TeV, we need a proton of at least PeV or a bit higher energy in a jet, and a photon that just happens to be in the X-ray range. And we can generally have these things, aside from accelerating protons, we can generally have these observables produced in almost the same region. So radio and X-rays come from synchrotron and synchrotron self-Compton emission, and the same X-rays, they interact with protons that are accelerated somehow to produce neutrinos. And the reason why we see both of, like all this emission on Earth is really because all of this is beamed along the jet, and for the sources that are aligned with the line of sight, we can detect them on Earth. And this proton, of course, kind of probably the main kind of remaining question here, a pretty big one, is how these multi-PeV protons get accelerated within central parsecs. Judging by like some rough estimates from the neutrino, like from constraining neutrino flux, so, at the very least, 10 to the 43, 10 to the 44 of the this kind of energy energy protons. So it's not the all protons, it's just the high energy protons. And it already means that a very significant fraction, maybe even the dominant fraction of the jet power is carried by these high energy protons. And even though we cannot reliably see and distinguish them in electromagnetic emission, they carry a major part of the jet energy, and neutrinos give probably the only way to observationally quantify them in the near future. Yeah, so even though as I told, all these kind of all these emission mechanisms can happen in the same region, they might not even be directly related. Like synchrotron emission doesn't care about accelerated protons here, or maybe of course these like single zone models, they are the simplest and easiest to kind of grasp, but the reality is definitely more complicated. And now we are also like hope to use the neutrino flux estimates as another very important kind of constraint on the multi-zone modeling. But this is really a very there is a lot of questions that can only be answered with more data or with some assumptions. Yeah. Just to sum it up, if you remember one thing from, if you take away one thing from my talk, I want it to be this. So neutrinos at 10 electron volts energies and higher, many of them come from blazars, where these neutrinos are emitted along the jet direction. And the blazars, so AGNs with a jet pointing towards us, they form a significant population of high-energy neutrino sources. Observational picture is becoming cleaner over the past few years. It stands the test of time. Even our first analysis on the population study was already more than 5 years ago, and we still see the correlation very consistently with new data. Given the fact that at these kind of close to PeV energies, we can only detect much less than one neutrino from each source, even for very bright sources, we crucially depend on population studies. We need to be very lucky to say something about an individual source, but population studies are kind of a guaranteed way to constrain the neutrino emission. This was kind of very impressive and surprising for me when I first saw it. The jets in neutrino-emitting blazars are extremely beamed, even compared to already highly beamed blazars. Yeah, and again, going to this kind of main standing question and what we can say about protons, we can already put these kind of important constraints, even though we don't resolve the proton acceleration question completely, that they need to be accelerated somewhere in central parsecs or even closer to the black hole. And they not just have these many PV energies in general, but some fraction of their momentum is along the jet, so that the neutrinos are come out beamed. So as for just a brief outlook for the future, I'm really looking forward for kind of finding other ways to other observational tracers of neutrino blazar connection other than beaming. And here, I think variability and like flare correlation should be the next step. We already have some kind of preliminary results for neutrino versus electromagnetic flares, but of course it's naturally more complicated than just positional analysis. It needs more neutrino data. Yeah, I won't repeat it again, but proton acceleration is a major standing question. And also, like really understanding other populations of neutrino sources and even neutrino-emitting agents. So here I really discuss and highlight and demonstrate the population of beamed agents that produce neutrinos. Maybe it's totally possible that there is another population of non-beamed agents, the same as we see in electromagnetic waves. Then there is a question of whether the neutrino fluxes is strongly flaring, like we see in gamma rays generally, or it is persistent and just slowly varying. Also, of course, a big question of what is the nature of neutrinos coming to us at even higher energies, like the recent Came3Net event at 100 PeV. I think these energies become even more challenging to produce even in very strong blazars. So it remains to be seen what is their nature. But yeah, I'm really looking forward for the next few years in the neutrino astronomy and multi-messenger connections as well. Thanks for your attention. These are the papers this talk is based on, and now I'm looking for questions, discussions, and anything. Thank you.
Hey, thank you, Sasha. It was a really interesting and great talk. So let's see if anyone has any questions. Okay, you can raise your hand or just turn on your speaker. But maybe I can ask my question first. Like it could be very naive, sorry. But I think it was at the beginning of your talk when you mentioned that blazars are well observed with VLBI. Or VLBI is so powerful, but I didn't get why VLBI.
Yeah, so the reason why VLBI turns out to be useful here is that it is kind of the only way to directly probe these parsec scales. And by probing, I mean it only sees the very brightest emission. VLBI just is not very sensitive compared to other telescopes, so it only sees the very brightest emission and only from the central parsec scales. So if you see a very bright radio emission, like synchrotron emission from the inner parsec scales, its brightness temperature can exceed like 10 to the 13 Kelvin or something like that. And really, the only way to get this brightness temperature is to experience relativistic beaming that boosts it. So it's kind of this two-step argument.
Okay. Yeah, got it. Thank you. So I see Paul has a question. You can go ahead.
Hi, Sasha. Thank you. I think it was a really interesting talk. One question I had was right at the beginning, you mentioned something about of the neutrinos you see, it was only about half of them come from astrophysical sources. I was just curious about that comment, if I heard it correctly. And then if it is correct, what is the potential source of the other half?
Oh, yeah.
Understanding of the other half.
This part is, I mean, the other part is much, much more understood. It is just our atmosphere. And the atmospheric neutrino flux is well measured at lower energies. Uh, I don't think I actually have a slide for that, sorry. But as you go to higher energies, the atmospheric flux just it's steeper. So at some point you start seeing like at least relative dominance of astrophysical neutrinos. And these hundreds of TeV is kind of the current observing capabilities of neutrino observatories is kind of the golden zone where you still have quite a bit of neutrinos left, so like several tens or hundred, and already about half of them is astrophysical. It's quite a lot. So typically, if you go to lower energies, you get like maybe 10% or 1% is astrophysical. The other part is atmosphere.
Sorry, and do you get neutrinos of that high energy coming from the atmosphere?
Yeah. There is in some of the so in one of the earlier IceCube papers, there is a whole kind of like overall neutrino spectrum, and they show overplot atmospheric and astrophysical so they feed the astrophysical spectrum basically by subtracting the well-known atmospheric spectrum from the observed one. And even at the highest energies, there are still a few neutrinos per year that are coming from the atmosphere.
Okay, and then how do you then tell the difference as to where they come from?
No way, really. They are exactly the same. That's why you need either population studies or even in individual cases, some statistical analysis, because the only way we can say that the neutrino is coming from some source or a set of neutrinos comes from some population of sources is through kind of positional or potentially temporal association. So the result I'm showing here, it is kind of a way to select like it can be seen as a way to select neutrinos that are coming from blazars out of the whole set of neutrinos. Basically, first what we do is just look at the just blazars that fall close to the neutrino detections in the sky, just positionally, and look at their average fluxes. And this flux happens to be much higher than the average flux of a just blazar elsewhere in the sky. And this correlation can, I mean, given that it's very statistically significant, it can only arise if some fraction of these neutrinos, like several, or like 10, maybe 15 out of these, they come from blazars. And yeah, we don't have any a priori way to distinguish really.
Okay, thank you. That is really interesting.
Okay, thank you. I think Sarah has a question as well. Please go ahead.
Yes, thank you, Sasha. That was a really great talk. I learnt a lot. I was wondering, could you tell us more about how often the VLBI for the observations take place? Because in the radio, we see examples of radio lobes showing us a radio galaxy that's in the plane of the sky, but more recently, the radio jet axis might have changed direction and is now pointing towards us, turning it into a blazar. So I was wondering if you could.
Yeah. So VLBI observations. So for the large sample for the large sample of like thousands of blazars, this is a complete sample in that it was observed once up to some like sensitivity of 100 something millijanskis, but this sample is not regularly monitored. It just
Right.
was observed kind of once, or some sources were observed several times. It's kind of a mix, but every source above some flux density was measured at least once. In terms of monitoring, we have this kind of to measure all these geometric properties and kinematics. We do monitoring within the Mojave team, and for this monitoring, you have observations several times a year. There is actually very careful considerations of like what sources you need to observe every month, what sources are changing slowly, you can observe them twice a year, and so on, to really observe as much as we can. And these timescales, observation timescales of like several times a year, they are guided by the typical kind of variabilities that we see in images. We see a lot of jet direction changes, but it's like it can be huge in the sky plane, but it is only like a degree or at maximum a few degrees in the like in 3D space over a few years. So
Right.
I think what you are asking, it happens on much longer scales, right?
Yes, yeah, that is the case. Yeah.
Yeah.
Thank you very much. That was awesome.
Okay, thank you again. And I don't see any other question or comments anyone would like to say.
Yeah, feel free to message me afterwards as well.
Thank you so much. Again, it was a great talk and I've learned a lot as well. So thank you, Sasha, and thank you everyone for joining, and we'll see you in the next colloquium.
Yeah, thanks everyone. Bye.
Thank you. Bye.